Alright, let's continue this with an example, and let's say that we have a multi-input, multi-output system of a car. We are interested in one signal, particular signal. It is, we call it as y of t in that system, and we look at all the possible inputs and we select only one input, u of t, and how this is influencing the y of t is shown by the schematic of what I have here is shown. Then, in order for us to obtain a model between the input u of t and output y of t, the conventional approaches exist. In mechanical systems, we have, for example, free body diagrams, and applying each component, since the system is linear and time invariant, using Newton's second law, and we try to look at the forces applied in each particle, and we write the equations corresponding to that. In this class, we are going to do something is kind of untraditional. In Nis's second chapter, briefly talks about this approach, which is using, without showing the graph, it is using the graph methods, and we are going to be going after theorem 1 using the node equations and try to look at the system equation, try to obtain the system equations using node relative variables. Since we are in the mechanical domain, our node relative variables can be taken as position or velocity or even acceleration. However, to make our transition a little bit operation a little bit more convenient, I'm going to be selecting the position as my node relative variable, and we will try to express it with respect to non-moving or inertial with respect to inertial frame. So we are looking in the schematics and or in the system, try to identify how many independent positions that will be measured, that will be seen, observed in the system. We have u of t applied to one part of the terminal K1 spring. So the input terminal is going to have a position independent than x. X and y are the two positions of masses m1 and m2, and other than that there are no independent nodes in the system. If I call the u of t node as node, let's put a name here, node A for this node. So the graph representation of this diagram will be, I have A here, node X here, and node Y here. These are the independent positions that exist in this system. The node A is excited by input from my inertial frame, and this is my u of t. Between A and X, I have K1, and let's call this spring K2, D1, or let's call this guy D2 and D1. And between X and Y, I have two components. I'm gonna place them in here. We have K2 and D2. At X, with respect to inertial frame, I have M1. The mass always defined with respect to non-moving coordinate frame, non-moving node, M1, inertial frame, and M2 also is defined with respect to ground. Between A and Y, I have another component. Let me show it here. This is D1. Now we have a graph view. Once we have this graph view, I said that we have a domainless system representation. To obtain the system equations using node theorem 1 and node relative variables equation can be obtained using a simplified approach. We have the equations, let's write it here, sum of all the generalized admittances attached to node, let's call this, make it generic, node I. For all k, we are going to be summing all the components, generalized admittances at node I, where we are writing the node equation for node I, minus between this node I and all the other nodes. If we have any components, we are gonna sum them for all k, all the generalized admittances of components between node I and j times xj here. I forgot to add times xi minus and minus. We do this for all the j's, all the nodes in the system except I. We'll try to find out if there is any components between node I and node j. We write the sum of all the generalized admittances between those two nodes. We are going to equate this sum of external flow sources at node I. Now, if I write this kind of clumsy looking set of equation, is not very difficult. For example, if I have to write for node x, the components attached to node x are k1, k2, d2, and 1. What the theorem is saying, that we are going to get the sum of all the generalized admittances. Let's call them uppercase yk1 plus yk2 plus yd2 plus ym1 times our independent variable x of s minus between node x and any other node. I have here yk1 times u of t or a of s. Let's call u of s here, minus between this node x and node y. Is there any component? Yes, there are two. We are going to be writing some of the generalized admittances yk of 2 plus yd of 2 times y of s. Here Y with subscript are showing the generalized admittances. This Y of S is just showing the position of the mass M2 equals. Is there any external flow source attached to exerted to the system? No, which is equal to 0. We have this first set of equation, and then we will repeat this for other nodes Y, and in some cases we'll do it for A, in some other cases it won't be necessary. We'll see that in a minute. It is just to give you this generalized approach. So in order for us to carry out with this generalized approach, all we have to do is define what is the generalized admittance in this in our system. So I can come here and make this definition of if in a particular domain we have let relative variable in S domain be R of S and flow or true variable be, let's call it T of S, then the generalized admittance is defined as Y of S equals the flow variable T of S over relative or across variable R of S. This is the definition. Similarly, I can make the definition of generalized impedance let's call this Z of S equals 1 over Y of S or R of S over T of S. For node equations, we are going to be using generalized admittances. For loop or mesh equations, we are going to be needing for each component generalized impedances, and we will look at this approach. We are going to apply this technique over and over in all the